Welcome to Office Hours. Today, we're going to talk about the evolution of the atomic model. The earliest recordings of atomic theory are from the writings of Democritus in the 5th century BCE. He was recording the teachings of Leucippus, the founder of the atomist philosophy. The early atomists believed that everything is made up of indivisible parts called atoms. The central idea of this philosophy endured throughout the 19th century and became formally recognized by the scientific community when English chemist John Dalton published a new system of chemical philosophy in 1808. In it, he states that all matter is made up of atoms, which are indivisible building blocks of matter and cannot be destroyed. He also stated that all atoms of an element are identical, and the atoms of different elements vary in size and mass. Finally, he restated from an early work that all chemical compounds are produced through different whole number combinations of atoms, and the chemical reaction is a result of the rearrangement of the atoms in the reactants to form the product compounds. Dalton's atomic model was broken apart when British physicist J.J. Thomson discovered the electron in 1897 while he was studying cathode rays. He determined that cathode rays were beams of negatively charged particles, and through careful calculations, he determined that these particles were much less massive than the smallest known atom at the time. He called these particles corpuscles, but the term electron, coined by George Johnstone Stoney in 1891, proved to be more enduring. The main problem with Thomson's original hypothesis is that he proposed that the electrons were the only parts of the atom, but it was well known at the time that atoms were electrically neutral, so he proposed that the electrons had to be suspended in a massless positively charged cloud to balance out the electric charge. This model is oftentimes called the plum pudding model because the electrons resemble the raisins suspended in the cake. Thomson's model was refuted by one of his students, New Zealand-born physicist Ernest Rutherford, in 1911, based on the results of two of Rutherford's students, fellow New Zealand-born Ernest Marsden and German physicist Hans Geiger, in 1909. The Geiger-Marsden experiment involves shooting alpha particles at a little piece of very thin gold foil and measuring the deflection of the positively charged particle. If the Thomson model was correct, they expected the alpha particles to pass right through with minimal deflections. What they saw was that most of the particles passed straight through, but some of them had some wild deflections. This indicated that the atom is not a piece of plum pudding, but rather it's mostly empty space with all of its positive charge and most of its mass concentrated in the center. Rutherford called this central concentration the nucleus of the atom. Rutherford was not the first scientist to submit a planetary model of the atom. In fact, Rutherford's model was inspired by the Saturian model proposed by Nagaoka Hantaro, a Japanese physicist, in 1903. He proposed that electrons orbited a large central mass that is positively charged. The electrons are then bound in their orbits by electrostatic charges. The main problem with this model is that the charge rings would be highly unstable due to the repulsive forces between electrons. Nagaoka abandoned this model in 1908, but Rutherford borrowed the model's aesthetic for his 1911 paper. The electromagnetic force responsible for these electron orbitals proved to be a very different type of interaction from the gravitational force that governed the planets. The planets are kept in place due to their speed and rotation counteracting the gravitational pull of other planets. But the moving charged particles emit electromagnetic radiation, causing them to lose energy, meaning that their orbits would eventually decay, causing them to fall into the nucleus. Nagaoka had done some pioneering work with optical spectroscopy, the study of the interaction between matter and electromagnetic radiation. But it was the experiment done by Niels Bohr and the hydrogen atom that took the atomic model to new levels. He found that when he passed an electric current through hydrogen gas, exciting the electrons, the gas gave off distinct spectral lines, indicating that the electrons couldn't continuously lose energy, but could only release discrete amounts. This led Bohr to propose that electrons organize themselves into discrete energy levels. Bohr was only able to prove this for the hydrogen model, and as spectroscopy technology improved, his model was shown to no longer be accurate even for hydrogen. In 1924, Louis de Broglie rocked the physics world by proposing that all moving particles display some amount of wave-like tendencies. This revelation helped physicists describe light as a wavicle, part light, part particle. In 1926, Edwin Schrödinger applied these ideas to electrons and proposed the Schrödinger wave equation. This equation was able to accurately predict the spectral lines of hydrogen and other elements, but it wasn't too easy to visualize. Max Born, a rival, suggested thinking about the probabilities of all states of the electrons instead of just one single state. Instead of stopping Schrödinger, this revelation of probability clouds allowed the energy levels from the Bohr model to be broken up into suborbitals. Thus, all the discrepancy of past models were neatly tied up, and for now, this is our picture of the atom. Thank you so much for attending office hours. If you like what you saw, please consider subscribing to the channel and hitting that bell to get notifications when new videos drop. I also stream office hours on Twitch and on Facebook. If you want more office hours, please consider becoming a regular drop-in by joining my Patreon or simply buy me a coffee. Support from viewers like you let me know that you want more office hours, and I'm happy to provide. Well, thanks again, and I hope to see you around.